Okay, our next speaker is Chenhao Zhang, who I believe is a student at Northwestern. Is that right?
Yeah, I'm a PG student.
Okay. And he's, you have to turn it on. There's a little on button. He will be telling us about hashline Karp, which is about formulating and testing, random testing NP reductions, which are otherwise notoriously hard to do. So I'll let you also give an introduction of yourself, Chenhao, to say what you do and what you work on. So Chenhao Zhang.
Hi, I'm Chenhao. I'm a PhD student at Northwestern, so I'm kind of half theory and half in the programming language. So today I'm going to talk about a work that actually combines a lot of knowledge, wisdom from our Racket community, which is a language for NP reductions, mostly for pedagogical purposes. So there's a kind of problems in computer science we call decision problems that they ask for yes/no answers. For example, I show you Boolean formulas, and I ask you, is it possible to find a true-false assignment to each of these variables such that all the clauses are satisfied? Of course, after staring at this example, you will say, yes. Why? You can basically find the assignment shown here, and after plugging this assignment into the Boolean formula and check, you can see that every clause is satisfied. Another example is this problem called the independent set. I give you a graph, and I give you a threshold number. Say here, in this case, it's 3. I ask you, is it possible you can find me a set of 3 vertices such that no 2 of them are neighbors of each other? Anyone want to give a try? Maybe what if I tell you yes, and I show you here's what I found? Are you going to agree with me? No, right? Because it doesn't match with the threshold number. What about if I show you this? You also say no, because, sorry. If I show you this, you will say no, because it does not satisfy the requirement that no 2 of them are neighbors to each other. If I show you this, you will also not agree, because it doesn't satisfy the threshold number requirement. So no matter how hard you try, you will find out you will not be able to find something that can convince me. So the answer will be no. However, if we change this threshold number slightly a little bit, then we'll get a yes answer, and you will be able to find something that convinces me. Another prominent example is a problem called Hamiltonian cycle. So basically, I give you a graph, and I ask you, can you find a circle that visits all vertices exactly once? Okay, for this particular instances, I can convince you the answer is yes, although this might be hard to eyeball it. But if I show you this, you should probably get convinced. So all these problems, they have some features in common. The common feature is that they are so-called NP problems. So what does it mean by NP problems? That for every of these NP problems, there is a verifier. So what does the verifier do? If you plug in any instance and proof of this instance being yes, the verifier can check in polynomial time whether this proof of yes, which we call certificate, is a valid certificate for that instance or not. So if for any yes instance there exists such a certificate, such it will get accepted by the verifier. And if there's no instance, no matter how hard you try, you're trying to push anything into the verifier to pair with that instance, you are doomed to fail. The verifier will forcefully reject them. Good enough. So reduction is basically a transformation between two problems, x and y, that takes an instance of problem x and spit out an instance of problem y, such that the transformation preserves the yes-no answer. So if you plug in a yes instance of problem x, it will spit out a yes instance of problem y. On the other hand, if you plug in a no instance of problem x, it should spit out a no instance of problem y. So why is this notion useful? It's prevailing in computer science. Is a very important tool for us to show hardness of the problem. How does it work? Suppose now we have a problem that we are not sure if it's easy or hard, right? It looks easy. Is it easy? In order to show that it is hard, what do we do? We find a problem that is knowingly to be hard. And then we construct a reduction from the knowingly hard problem to the problem that we suspect is hard. If the reduction is correct, then boom, we know that the problem we want to show is actually hard. The reason behind that is if you are able to solve the suspecting problem in a reasonable amount of time, you basically compose the reduction with any algorithm you propose. Voila, you get a solution for the hard problem that is known to hard. And we know the problem that is known to hard is unlikely to have an efficient solution. So we know this must not be the case. So the problem that we are concerned must also be hard. So reduction is something standard we teach in algorithms. But the problem is that pen and paper reductions are often very subtle to check. And even sometimes instructors made mistakes. So our solution to this is why not just write reductions as programs and the random testing them. So we have designed and implement the language Carp on top of Racket. Why its name is Carp? Because it is named after Richard Karp, which was a pioneer, of the complexity theory and had the ideas of using reduction to show in hardness. Now I'm going to give you a demo of a reduction done in Carp from the example, the problems we have just seen, the 3-set problem and the independent set. This okay? Maybe I need to have the font larger. Okay. Is this good? Maybe larger. Slightly. Okay. I guess this is good for us. So in order to formulate the reduction in Carp, what you need to do, the first thing you need to do is to specify the problems. Okay, you need to specify the problem you reduce from and you reduce to. To specify a problem in Carp, you will do two things. First, you will define the data structure for that problem. And then you will define the verifier. So how does it work? So Carp has two sublanguages. The problem definition language is where we define the problems. So in order to define this reset problem, because we know this reset problem has the structure of CNF, Boolean formulas, and it has a assignment in it. So Carp provides these built-in data structure libraries. You can just import them. And then we use the decision problem language construct to define our problem. For example, here, 3set. We give it a name, 3set. And the instance is pretty straightforward, because 3set, basically, the instance is just a CNI formula with arity 3. So you can basically utilize the built-in structure, built-in CNF library to define your problem. And then for certificate, the certificate of 3set problems is a mapping, is an assignment from the variables of the CNF to the set of booleans. Basically, you want to assign each variable to a boolean. So you will define your certificate in this particular way. Now going to the certificate verifier. This is also pretty straightforward. What you do is how a human would check certificate is indeed a certificate for instance. What you do is basically you go over all the classes. You assert that for all classes, if there is some literal such that this assignment will make at least one literal satisfied, which is to say, if there is x literal, it is a positive literal, and the variable of that literal under the assignment is assigned to be true, or it is a negative literal, and the variable under that literal is assigned to be false, then that literal is satisfied. And if all the classes has at least one literal that is satisfied, then we get a valid certificate. In the same way, we'll define our independent set instance, independent set problem. So slightly different in independent set, we have the graph structure. Of course, this is also provided in the built-in library. But now we have two components in the problem instance. We have a graph, which is undirected. And we also have a threshold number, which is just a natural. And the certificate is basically a subset of the vertices of this graph. And then to check a certificate, whether the certificate is a valid certificate for a given instance, what we do is basically we check two things. If the threshold constraint is satisfied, if there's enough vertices in the proposed certificate, and if the certificate is satisfying the constraint that no two vertices in them are neighbors of each other. Fair enough? After defining these two problems, we can proceed to the reduction. So for the sake of time, I'm not going to talk about the exact transformation, but the way you do it is you import the two problem definitions. And also in the reduction language, there will be a language construct for you to specify this transformation and random testing. For example, here we have a correct reduction. Basically, it transforms the CNF on the left to independent set instance on the right. So if we run the program with the correct reduction, I have to run this for you. It will randomly generate 10 instances. And after the random testing, you conclude that it is correct because you cannot find a counterexample that violates this property. However, here I also have buggy reduction. The buggy reduction basically forgets certain essential parts in the transformation. So if we instead run the buggy reduction with random testing, it immediately finds a counterexample. And here we have a visualizer, basically shows what's going on here. It shows there's a counterexample, and this is the graph of that counterexample, which is exactly it misses certain essential component for the reduction to be correct. So for the remaining time, I'm going to highlight a couple of important ideas behind Carp, which combines a lot of interesting ideas and wisdoms from our community. So basically, we have utilized property testing. We also have encodings based on the software-aided programming language Rosette, and then we also draw inspiration from the recent, not so recent work of building type systems, and also gradual typing to ensure the correctness when values travel through all of these components. So for the sake of time, probably I'm going to highlight the first 2 points. So as we know that in order to check the correctness of reduction, the property we need to check is whether a yes instance is mapped to yes instance, and a no instance is mapped to no instance. So we need to generate, we need instance generators. So the way the instance generators is derived from the problem definitions is that we have the problem definition, problem structure expands using macro to carry out, that carries particular information, and it will expand to instance generators. So we can have random instance generators to produce rich enough instance for the testing. And then in order to check if our instance is yes instance or no instance, we need the solvers. So the way we derive solvers from the problem definition, particularly from the verifier and the problem structure, is we build this process on top of the software-aided programming language, Rosette. So basically, the architecture works in this way. So we have a verifier in Carp, and then it will compile to the code in software-aided programming language, Rosette. And then the Rosette symbolically executed the code and generate queries to SMT solvers. And SMT solvers find, and for example here, for example, suppose we have a set. We want to find a set. We want to find some subset, which, like in our independent set example, we want to find a certificate, which is a subset. And it will turn into some internal encoding in Rosette, which in turn becomes SMT formulas for the SMT solver. And the SMT solver will solve the formulas for us. And again, it will turn back into internal encodings in Rosette. And then we translate the internal encoding back to the higher level abstraction we have in our verifier language. So for the remaining time, let me highlight the most exciting thing I want to talk about in this work, is how actually we encode various of these high-level structures in Rosette. For example, sets. As we know, for people familiar with Rosette, the primitive solvable structures or solvable objects in Rosette are in integers and booleans. So basically, you can create these primitive variables of these types and ask solvers to directly give answers to questions around these types. That's all of it. You can't have a complicated data structure directly feed in the solver. For example, in our setting, we have sets. But if you want to write code like this, unfortunately, Rosette won't let you do it. It will raise an error because it is not directly supported by the SMT solver. So we need to find a clever way to encode these higher abstraction data structure into these primitive data types that the solver natively supports. So let me use set as an example. For example, suppose we want to represent a set. What is the solution in Karp? So in Karp, we make assumption that every set is a subset of some finite ground set that we are concerned. For example, now we have a set. We assume it is a subset of -3 to 5. Then for the set -3, 1, 4, it will represent it as a hash from integers to Boolean. Those elements that are in the set will have a value true, and those elements that is not in the set will either not present or it will have a hash value of false. And the keys will basically be the elements of the ground set. So all these three representations will be valid. And then in order to solve for a symbolic set, suppose we want to solve for some unknown set that is a subset of this ground set. What we will do, if we know some partial information, we know for sure that -1 is there. We will assign true to the hash value corresponding to -1. For the remaining elements that we are unsure whether they're in, we will have a symbolic Boolean variable, which is a primitive variable that is native supported as the value of these elements. And then in order to generate a constraint, like is 5 a member of, if we ask if is 5 a member of S, we want to have a constraint like that, we can basically just call hash ref. In the case the set is concrete, in the case that we have all the information, we directly pull out that Boolean value. In case it is unknown, we will get a symbolic value. And in this way, we will be able to turn these kind of queries into primitive queries that Rosette and the SMT solver can support. In the same way, if we want to ask questions like, what is the cardinality of a particular set? We will also able to turn these kind of questions to formulas and encodings that is native supported by Rosette and the solver. So probably that's the part I would like to talk about. And now we have already released Carp on the Pocket server. So do please recommend it to instructors you know that teach the algorithm. So we hope to see this get adopted and relieve the burden of both algorithm instructors and TAs. Thank you.
Okay, we have time for maybe 1 or 2 questions. I guess I'll start while we're waiting. I was just wondering, do you imagine this having research applications in addition to teaching applications?
I mean, I guess for research applications, it's mostly about expressiveness. Okay, if we can express rich enough problems, it will have some research applications. So if we can express problems that people are interested in research, or the people, or on the other way, the problems that people are interested in, they're actually used in their research can be expressed in the framework, then it will be useful. So it's not, I guess it's not, the line is pretty blurred.
Wow. I just want to say this is really cool. It's all about taking the power of programming, something that we know how to do really well, and apply it to something that is, as you said yourself, genuinely difficult about algorithms, and bring all the tools that we know about and love about programming to bear to that other domain. I think that's really, really cool. Now, you talked about giving that to instructors for algorithms courses. I believe you've done some of that yourself. Do you want to say a little bit more about how you've been able to deploy this in actual classes?
So basically, the way we deploy this mostly, because, okay, the way we had basically labs, assignments for people, I think the philosophy behind this is not using this as an auto-grading system, but rather give students more chances to actually work on a solution and stumble upon it and get feedback, because these solutions are pretty subtle. In programming exercises, there are a lot of chance to redo it. If they find a problem, they have a chance to debug and fix the problem. This is something I feel like, as a serious person, which we don't have that much resources, so we don't have that much energy to keep the students, because reading the proofs or correcting proofs is kind of takes a lot of effort. So I guess that's the way we envision the tool will help the students.
That's great.
Time for one more.
Hi, thanks for the talk. You talked about proving these things to be incorrect. I'm wondering if you thought about, or if it'd be possible to prove the reductions to be correct with some kind of dependent type theory, or maybe you don't have to go that far. But
this is a very good question. We're getting this kind of questions a lot, of course, right? Because currently what we do is simply random testing. I guess maybe it's a little bit ambitious for reduction, because it is pretty involved. And these dependent types are based theorem proofs. They require you to formulate things in a particular way, otherwise they will not accept you. But as we are seeing, we want to give people flexibility of encoding stuff in different forms, right? We have this language, you can actually, one problem can be formulated in multiple ways. So I guess a less ambitious goal thing we are trying to do on this path is we are making some attempt to see if we can prove the correctness of dynamic programming solutions. That's something we're still working on. It's like that because it has more structure, so it's easier. It's supposed to be easier than reduction. Of course, it's still not easy. We made some attempt. It's still kind of difficult, I would say.
thank you.
Okay, Chenhao, you have more questions on the live stream, so you can look at them later. But let's give it up for Chenhao, everybody.